another seminar of our cycle of seminars of the astronomy department. Today we are very pleased to have with us online Marina Bianchin. Many thanks, Marina, for accepting our invitation to be here with us, sharing your work. It's a pleasure. So let me briefly introduce Marina to you. Marina got her bachelor, master, and PhD degrees from the Federal University of Santa Maria, which is located in the state of Rio Grande do Sul. And now she's a postdoc researcher at the University of California, Irvine, in the USA. Her research involves extragalactic infrared photometry and spectroscopy, and currently she's using JWST data, and she's a member of the Great Observatories All-Sky LIRC survey. And Marina also participates in outreach initiatives. And today she's going to present multiphase gas kinematics as a tracer of AGN-driven outflows across different wavelengths. And before we start, please, those who are in Google Meet, turn off your microphones and cameras. And if you have a question, you can raise your hand in the Google Meet, or you can write it down in the YouTube chat, and we will ask the question after the talk. So, Marina, whenever you're ready, you can start.
Okay. I'll share my screen. Okay.
So can you please wait a little bit, Marina, because there is a problem with the YouTube? Just a little.
Okay.
Couple of seconds. We are trying to see what is happening.
No problem. Can I go at this screen this way, or should I turn it off?
It's fine. You can start. I'm sorry for that. You can start.
I can. Okay. Thanks everyone for. Oops. 1 second. Thanks for having me here. It's a pleasure to be talking to this audience, to be talking to people in IAG. That is an institute that has a great place in my heart, especially because I had friends there. One of my thesis committee members is a professor at the IAG, so I have a special connection with your department. So today I'm going to talk about the multiphase gas kinematics as a tracer of AGN-driven outflows and inflows as well. That wasn't the main topic, but it kind of appeared afterwards, that across different wavelengths. So Maria already gave a brief background. So this is a small background that I won't go through everything. But besides the extragalactic research, I also did some analysis of embedded stellar clusters. So if you have questions and want to talk about embedded stellar clusters in the near infrared using large surveys, I can also talk a little bit about that. And mostly I'm involved in everything was near infrared and mid infrared. Now mostly mid infrared, but I also did a few things in the optical as the quasar feedback survey that I'll be talking here today, and some analysis using GMOS data of targets that will be observed with JWST. So I guess this slide is not so useful for this audience, but I had this from a previous talk and I recycled that. Where the university is located is in the southernmost state of Brazil, right in the center, in the middle of Brazil. And to the US audience and the European audience, I usually say that it's closer to Uruguay and Argentina than it is to the rest of Brazil. So it's kind of unusual place to be. And here are some pictures of the city. If sometime you leave São Paulo and go to the south of Brazil, you also get to see a nice view, especially the planetarium. That is this round building that I really like. And now I am in a completely different place. I am in UCI, that is one of the 10 campuses of University of California. It's the region called the Southern California part that is exactly in between LA and San Diego. So here I pinpointed that on the map, and here's a picture of the campus that I took 2 weeks ago. That since here is spring has started, we have lots of flowers around. But going now entering the science part, this is the outline of my talk. First of all, I'll be talking about very briefly about what is an AGN, very quickly, what is AGN feeding, and what is AGN feedback. Then I'll be moving towards my actual research works. One of them, mostly this is ongoing research. One of them is about the quasar feedback survey. I'll be talking about the survey in general and the research that I did within that. That is mostly the analysis of type 2 sources and understanding the kinematics of these galaxies. Then I'll compare this with the AGN-NIFS, that is the near-infrared survey using NIFS, that is an instrument on Gemini, to understand the kinematics of closer sources that are galaxies that are closer to us. And then I'll move to the JWST part of the talk. We use for this, I will show results for NGC 7469. It's a really cool galaxy that probably you saw pictures of it. And I'll be talking about the near-spec galaxy, near-spec data analysis, but also the published MIRI results, so near-infrared and mid-infrared. So my title says across different wavelengths, and my across different wavelengths go from the optical to the mid-infrared. Is kind of a limited multi-wavelength analysis, but I'll try to show you that even with it's not gamma raised to radio, it's still really interesting, and we have a bunch of features and things that we can analyze within this data range. So what is an AGN? Active galaxies are galaxies that have a supermassive black hole, as shown here is in this artist impression of what should creating supermassive black hole should look like. Accreting means that somehow the gas that is on the galaxy lost angular momentum and is going towards the center and is entering the supermassive black hole. But before it enters the supermassive black hole, it gets hot, it turns out to be plasma and emits lots of radiation, in some cases more or less, depending on the type of the galaxy. And this also can create radio jets and other energetic phenomena that we believe influences the fate of the galaxies, influences how the galaxies evolve. In some cases, like the quasars stand for quasi-stellar radio source, even though most of the quasars, not all of them are radio out galaxies. They can be, the nucleus can be 100 times brighter than the host galaxy. That means in some cases, we only see the point source in the nucleus, and we don't even see the host galaxy before doing some kind of analysis to remove this point source. So here I'm just listing some kinds of active galaxies, Seyfert/quasars, depending on the luminosity of the galaxy, radial galaxies, for example, Centaurus A, that we see the large bubbles, liners, and some BL-like objects that we also see extreme radio emission in these objects. So now I'll be moving to AGN feeding, because in order to have accreting a supermassive black hole that is accreting matter, the matter has somehow to get to the center and to the supermassive black hole and feed it. So a few processes can lead to matter going towards the center and feeding the supermassive black hole. I really like this figure from Stark Bergman and Schnarr-Miller, 2019, where they summarize some of the processes that can make the gas that is either in the ISM, the intercluster medium, or within the galaxy go towards the center. Especially at the galactic scale, that is the scale that I'm mostly familiar with analyzing, and the inner 1 kiloparsec of the galaxies. Usually the gas flows through the spiral arms or nuclear spirals or nuclear bars, but also mergers can influence. The mergers are an important part. They can influence how the gas goes and loses angular momentum and goes towards the center. And here is an example from this galaxy called NGC 2110, where we see this spirally pattern in the velocity field of the molecular hydrogen, and this is interpreted as gas, as a nuclear spiral and gas flowing towards the center that will ultimately feed the supermassive black hole. So we got the gas went to the center, the supermassive black hole is triggered, or it is continuing to get the fuel, to provide the fuel for the agent to continue to be active and release energy. But what happens then? The gas got there, created the accretion disk, and then what? Then what happens? It's called what I'm highlighted here in this yellow box. It's called AGN-driven feedback. AGN-driven feedback. I really like this definition that is short, that says the effect that the agent can have on the host galaxy as a byproduct of the supermassive black hole feeding. So any effect that this agent can cause on the host galaxy is understood as feedback. Why do we care about feedback? We care because some models, when we try to analyze the luminosity function of galaxies, there is the number of galaxies per bin of luminosity. We see some discrepancy, and this figure here is from 2003, so it's quite old, but it's kind of a classical figure to show this. On the higher luminosity end, and remember, astronomers use inverted numbers, so higher luminosity means more negative magnitudes. We see this discrepancy between any model of that try to reproduce the luminosity function of galaxies, that try to reproduce this dropout to the higher luminosities, but they can't. And the ingredient these authors propose, and many others after them within simulations, is that the feedback may be causing that. But the feedback is kind of an ingredient that is put on the models, but people don't really understand what it is and on simulations, and it's hard to quantify. So that's why we observers come into play, try to provide the numbers for that. And one thing that can provide these numbers is understanding the AGN-driven outflows, or AGN-driven winds. Some people call them winds. There is matter that is pushed out from the edges or some regions of the accretion disk to the outer parts of the galaxies, or even just to the inner parts, and disturbs the gas. Many different phases, many different features can happen. And and this figure here kind of summarizes that. That is the decoupling efficiency between the outflow and the galaxy. And here comparing with submodels. So with the dots, the points here are observed from observations, and the lines come from modeling. So different modelings, different theoretical prescriptions derive different values for this coupling efficiency, and these hydrodynamic simulations, we think they are the kind of the most accurate ones that we have. But when we compare to the data, some galaxies that are luminous, are very luminous, that we believe they should have more, the outflows should be more powerful, more efficient. They are less efficient than what the models predict. And maybe because this is only the kinetic energy, we're not accounting to the radiative processes. There are many factors that that come into play, and probably these are also efficient, but in another different way that we don't fully understand yet. So now I'll move into the actual data. This is about the quasar. First, I'll start with the quasar feedback survey. That is the idea of this project is just a quick look on the kinematics of type 2 sources. So here I'm showing one example of one of the galaxies that is on the survey that is called the teacup galaxy. You see the handle of the teacup here. And a quick summary of the sample. The goal is to spatially resolve galactic scale feedback in local high-Z analogs. This means that these galaxies, they have luminosities that are similar to the luminosities you see here. The O3 luminosity is higher than 10 to the 42 ergs per second. So the really the edge of the Sloan digital sky survey luminosity. But they are analogs to the cosmic known redshift 2 galaxies. Mostly they are radio quiet, so they are not powerful radio sources, although they have radio emission. And in our analysis, we use MUSE data to analyze these galaxies. And, in most of them, the full extent of the galaxy, because the MUSE field of view is large. Here I'm showing the same galaxy, the teacup galaxy, seen with MUSE. This is a pseudo narrowband image, just in the region of the O3 on this spectral region, H beta, and the two O3 transitions. And I'm showing the distribution of the gas of this galaxy. You see the handle, and on the contours, you see the radio data. So the idea here is to quantify the outflows, to quantify these extreme outflows, and try to understand what they are doing to the galaxies. We use a non-parametric measurement that is called the WAD. That is a proxy for the is a proxy for the width. It's the width of the line that has 80% of the flux, and we use that as a way of not depend on fitting multi-Gaussians and understanding this component here represents the disk. This other component, this is too complicated for the sources, that most of them are mergers or are ongoing extreme things are happening to them. So this is kind of easier, and this is the equation that we use to estimate the mass of the gas. And here is the density that I highlighted, that we derive it for most of the galaxies. I don't remember if for this one is the case. From the we derive them from these two argon lines we using PyNet. So here is an example of the same galaxy, the teacup galaxy, the kind of maps that we derive from our analysis. This is the W80 map, and here I'm showing the stellar continuum, the flux of the O3, the centroid velocity, and V10, that is the velocity at the 10% of the line. And the interesting thing here is where the radio emission peaks, and where it's mostly where the W80 is higher, but not and kind of perpendicular to where the W80 is higher, and we see some cool things going on. But we use these quantities. The maps are just to understand the distribution, but we also derive, we create radial profiles. These radial profiles, they show, these are for all the galaxies, they show this interesting pattern where the mass outflow rate, that is the amount of gas that is pushed out in a certain period of time, we slice the emission this map in different slices, in radial slices, and then we compute this mass outflow rate profiles, and we see they are higher at the very center, and then they drop out to the outer parts. Some drop out faster, and others, they are more flat. But this is interesting because it agrees with simulations. And two explanations arise to why they look similar. Maybe because the O3 clouds, they are being destroyed when they are reaching the halo of the galaxy, because this is 25-30 kiloparsecs, so it's really far away from the center. Or they are being destroyed, or they are being slowed down. So we don't know what exactly is happening, but these are the two hypotheses. And we also see a large scatter on this scaling wind relation that was proposed in 2017. Our data are the yellow and the green points, just two different ways of deriving the mass outflow rate, but they are kind of consistent. And we see that the numbers we derive are consistent, but they show a big, large scatter. And these other points I will explain later. The gray points I will explain later what they mean. So maybe this relation is not so tight relation as people thought before, but there is still some kind of trend, but it's not that obvious. I'll stop for a second. I'll talk now very briefly about the AGN-IF survey. The AGN-IF is kind of a similar approach of the quasar feedback survey, but with completely different selection criteria. These are 33 nearby Seyferts that were selected through their X-ray emission. So they are true AGN in the sense that they have confirmed X-ray emission. The observations were carried out with NIFS. NIFS is also in IFU, but in Gemini and on the K-band, and at much higher spatial and spectral resolution, with the caveat that it's a much smaller field of view. We also use this non-parametric analysis, where the W80 is adopted as the proxy for the outflow velocities, and we define these disturbed regions in a similar way to what was done to the quasar feedback survey. And we also see this large scatter. So this data, the gray data points on the previous plot are mostly the same gray points that appear here, plus the points, the blue and red points that are on this plot. And this is for the ionized gas that was traced by Berkeley gamma emission, and this is for the molecular gas. For the molecular gas, it seems like there is a trend, a more clear trend, but for the but for the ionized gas, it looks like there is a trend, but the scatter is huge. So maybe the correlation still holds, but the scatter is huge due to the way people estimate this outflow masses. And now I'm going to move to the JWST results. And this is a very cool picture that is put up together of NGC 7469, and I think you probably saw this picture before. And I'll talk about generally about the survey, and then a little bit about the near spec data analysis and what we obtained with MIRI. So just a brief overview about the project itself. All this data, the MIRI and the near spec data, are part of one of the projects that were selected to the ERS program, Early Release Science. The proposals were selected in 2017, so 5 years from the selection to when we actually got the data. They were selected to be showcases of the JWST capabilities in 60 different science categories. And the name of the proposal is a JWST study of starburst agent connection in merging lurks. So we have imaging and we have spectra, spatially resolved spectra for these 4 galaxies. We got all the data already. Some of them is published, and some of it is published, but some analysis is still going on. And here I'm just showing an example of the galaxy. So JWST 86, you see this is the hidden nucleus. We are not pointing to any of the other parts. We have the imaging for everything. This is 7469 with the bright inner star forming ring. VV 114, the dusty obscured nucleus that we still don't know if it is an AGN or not. And then NGC 3256, we see there is 2 nucleus, so that's why 2 pointings. And oops, sorry. And here I'm going to show you some results with the near spec analysis. And the cool thing about this galaxy is that it is a so rich environment where we see different things going on at the same time. So here on top here, I'm showing the flux maps for the iron Paschen alpha. The Paschen alpha is a hydrogen recombination line. And for the molecular hydrogen, we see this clear star forming ring as in the previous slide that we saw in the Hubble images, but we also see it in the iron and in the Paschen alpha, but we don't see it in the hydrogen molecular gas. And we see this cool features in the velocity dispersion map. That is the gas, the dispersion, the width of the line. So this was seen with MIRI, but none of these cool features were seen before. So here I'm doing, if this slide let me do what I want. I don't know why they are not behaving the way I expected. Sorry. We see this cool spiraling pattern on the inner part, and we still don't know yet what it is, but we think it could be a gas inflow that is going towards the center and is being traced by this inner spiral, although we don't see a clear feature on the velocity maps. But we think this could be a gas inflow towards that is going towards the center. So this could be not a gas outflow, but actually a gas inflowing to the center that it's keeping the AGN the way it is. And we also analyzed the gas excitation. This is an excitation diagram for those of you that are that know a little more about the optical wavelengths. In the optical, we have the BPT diagrams that are really well known. In the near infrared, we have this diagram that I don't know if it has a name to it, but it uses the iron to the Bianchin beta line, a molecular hydrogen to the bracket gamma, and since we have spatially resolved data, we can then plot where these data points in the diagram appear spatially, and this is the magenta and the red points. They would well be called AGN-like points, but they actually we divided them into separate regions to understand better, and we see that the higher ionization is closer to the nucleus, and the ring really shows a star forming kind of profile, star forming line ratios. So we are seeing a stratified thing where the radiation field is harder, closer to the AGN, and then it dims and has values that are really consistent with star forming where it should be in the star forming ring. So the analysis of this is undergoing, so stay tuned. I don't know exactly when, because it all depends on co-authors and publication times, but stay tuned. Something cool will come out of that. And here, since I'm entering the mid-infrared range right now, this is just a comparison between what we had, that is this purple dotted line with Spitzer, and now what we have. So this picture really this image really shows what we had. Spitzer was cool, but for example, this example here, the argon 2 line, this is a molecular hydrogen line right next to the argon line. We had one bump in the Spitzer data. And now we are resolving these two different lines. Same thing with the pH features. We are seeing the lines that are on top of the pH features. This was impossible with Spitzer before. So this is I think this figure really showcases the power of JWST, especially in the mid-infrared. That before the best we had was Spitzer, and now we have even better data. And now, on the last minutes, I'll go through some interesting results that we already published about the same galaxy, and this is 7469, but with MIRI. And in this case, we only analyze the channel 1 data. That means just this bit here, just up to 5 to 7 microns. That is just that part of the spectrum, because we had the higher spatial resolution, and at the time some of the other wavelengths had problems with the wavelength calibration, and we didn't really trust them. So that's why we focused only on the shorter wavelengths. And here is you can see the similarities between the previous and this figure, but the previous one with near spec was much more the ring and the structures were much more clear. It looked like I blurred everything, but I didn't. It's just a matter of resolution. And so we saw similar things on the distribution and the way the gas behaves, and we also see this cone-shaped thing on the velocity dispersion of the A2 that we understand traces shocked gas. And here on this outflow and shocked gas part, we analyzed the magnesium 5 line, that is a coronal line, a line that has a high ionization, more than 100 EVs, and we see it has an extreme bluing, and this extreme bluing reaches velocities up to minus 650 kilometers per second, and is extended to the east. So we see it on this side of the galaxy, opposite to this side, where we see this enhanced velocity dispersion on the molecular gas. And this is a correlation that between the luminosity of the molecular gas to the pHs, and also the iron. And this diagram it shows this diagram is kind of a shock diagnostic. The higher any of these two ratios is, the more likely this gas is being excited by shocks. And so we are really confirming that the western part, where we see that enhanced dispersion in the molecular gas, is tied to shocked gas. So here is the final scenario where this shows here the contours of the magnesium 5 line, and this bump here, this extension to the west, and on the others to the east, sorry, and to the other side we see the enhanced velocity dispersion, that is the shocked gas. This means that we see an outflow that is coming towards us, so because it's on the blue side of the spectrum, it's coming towards us, and the red part of the outflow that we don't see is almost entering the screen to the other side, but this is causing is disturbing the gas that is surrounding it. It's hitting the molecular gas. That's why we see that signature in the molecular hydrogen. So to summarize everything, because I talked about a bunch of different topics, we see this large scale, tens of kiloparsecs radio outflows that are consistent. They agree, at least in the qualitatively in the shape. They agree with simulations in the quasar feedback survey sources. So these quasars, they are injecting mass out to the outer parts of the galaxies, but with rates that are consistent with local Seyferts. So we think as quasars are really powerful, bright. They are really powerful and bright, but they are pushing and putting mass out to the outer parts of the galaxies, that is in rates and with powers that are really consistent with local Seyferts. So they are powerful and bright, but to what extent we still don't know yet. On the near spec data is revealing really cool things, especially the stratified ionization structure that we see, but also the inflow that we couldn't see with MIRI because we didn't have the recombination lines. And I also wanted to do some quick advertisement. That is for you to stay tuned, because we got the data for two other ULERGS. My supervisor is the PI of this program. That is VV340 North. We have really cool data that I wish I could share the plots with you, but I can't yet. But we are seeing extremely interesting correlations between multiple gas phases and previously unseen features that in the radio especially, but in the near spec, in the MIRI data, sorry, as well. And the UGC 5101, we also have some cool results coming soon. And these other two programs that are also targeting outflows. One of them is led by my PhD advisor, that we are going to look at the molecular outflows in more nearby sources that are through AGNs, and the other will look at molecular gas and how it behaves in cosmic known sources. So very different ranges of redshifts, but in all of them, the message is trying to understand exactly how much the fact that the galaxy is active is impacting its fate, and how, if we can create a common story and put constraints on data between things that are on the cosmic known and things that are that are nearby. So I think that's it, and thank you again.
Thank you. Thank you, Marina, for this great talk. Thank you very much. Let's see if we have questions here from the audience. Okay, I will start with a question. I am just curious about how you define the tracers for star formation. For example, in the you show in those plots.
The diagram that I showed, the tracer for the star formation.
Yes, exactly.
You mean
that
okay.
How it relates with the physics.
Okay, so those hard lines that you see in the plots, they don't come from models, from photoionization models, because photoionization models, I think they could be extended to the infrared. I'm not a specialist on that, but usually they are done, and they work really well in the optical, because it is where most people had the data to calibrate these models. But specifically to that, those hard lines, they came from empirical data. So those points were defined because those lines came from observing, I think it was galactic or extragalactic, most certainly galactic HO regions, and measuring the line ratios for HO regions, and then putting that, and we know these are HO regions, they are star forming regions in the galaxy, so we understand star forming sources in other galaxies should have the same line ratios. So they are empirical, they don't come from modeling.
Okay, I understand now. So you just take regions where you actually have star formation, and then you say, okay, we would expect a star formation within these rates, and then you just use that to calibrate your data.
Yeah.
Okay, great, thank you. So I think there is a question there in Google Meet. Betch, hi.
Oh,
yeah.
Hi, Marina. Excellent talk, fantastic results. And just to let you know that we are currently, we have performed MADD simulations of this sort of systems, exactly where you have the AGN activity versus the star formation in the nuclear region of the galaxies. And we see in our maps, in face-on maps, we see these rings, these star-forming rings and their shape is very similar to the pictures that you showed.
Oh, this is cool.
Yes, it's very cool. And as a matter of fact, the shape of these rings depends on the star formation rate of the galaxy and the AGN power and the opening angle of the AGN wind, let's say. So, and we have swept a parametric space with these quantities. So we have several different maps of these rings depending on these conditions. And it's very interesting because it's really, you know, it is really a combination of the two effects of all these ingredients. So the star formation driven wind or starburst driven wind that is caused by the evolution, the star formation of the system, and the AGN power and opening angle. So it's very nice. We are finishing a paper right now with these results, and as soon as we have it submitted, actually it's ready. We are about to submit it. Actually, it's a long, you know.
I can imagine it is long. Just for you talking all these facts that are put into the models, but it is cool to see that. Maybe we can talk later about that, because if you are seeing that the same effect, the same shape, it is cool when this galaxy is a perfect showcase of a nuclear starburst ring with an AGN. It is one of the most clear examples of that.
Yeah, it's amazing. I mean, of course, I will contact you. Actually, this is the work from a PhD thesis from one of my students, and I will let you know as soon as we have this paper submitted. I send to you, and of course, we are going to be glad to discuss. And we are going to quote this source as well, because I took notes from your presentation, and I will get in contact. Okay, Marina?
Okay, thank you.
Thanks a lot for a very, very nice presentation and results. Great.
Thank you.
Okay, so thank you. Let's move on with more questions here.
Hi, Marina. Thanks a lot for the talk. Very rich talk. And my question is about the simulations or our theoretical understanding. You mentioned in the beginning that some features, the simulations, the models, still cannot capture the entire physics, cannot reproduce some features of this AGN, this feedback. Would you have some guidance of your opinion, what the people doing simulation should try to looking for from this moment with all the data we have now? Which direction is missing for people to explore?
So, interesting point, because I was in a conference last month, 1 month exactly ago, where we had a discussion about exactly the same point. During the conference, people had different views, and people say, we know everything about mass outflow rates, we don't need anything more, it's solved. And other people are like, we don't know anything, we are still trying to understand. In my point of view, from the simulations, what is needed, and some people are actually working on that, is trying to capture the multiphase nature of outflows. And either I'm not a theoretician simulator, so it's hard for me to exactly explain how you should do that. But outflows do not come in a single flavor; they come in different shapes and different phases and different temperatures, and for us, we are still understanding, for example, the colder molecular outflows are just being unveiled, and people didn't even start understanding them within the mid-infrared range. We have ALMA that has CO, that is really cool, but with MIRI, we are starting to see things that are kind of in between ALMA and the near-infrared, but we see outflows, really cold outflows that extend to the very large distances in obscured nuclei, really cold outflows. We see those. We see powerful things, bubbles in gamma rays. We see the classical biconical shaped in the O3. So maybe the simulations should capture, not necessarily simulate that, but take into account all the different phases that we see this phenomenon happening. We see outflows that happens in ionized gas, in molecular gas, and they don't have the same rates, they don't have the same velocities, sometimes they don't even have the same opening, they don't have the same opening angles, they are complex. So I don't know exactly how the simulators should take this into account, but we see this in data. And say that the outflows are represented by one number, I think it is too simplistic, because we see them happening they have many views and many, depending on the system that you are looking at, within the same system, the atomic or molecular species that we are looking, we are seeing different things. So maybe trying to capture the multi-phase nature of what is going on could be helpful.
Thanks. Very interesting. Like multi-fluid simulations, not only the chemical composition, but also the dynamics of each phase. I see.
Yeah.
And from the also the modeling about the radiative transfer part, is it satisfactory? What is have been done?
I cannot say much about that. That is something beyond the things that I have explored in detail until now. So I cannot say, I cannot speak much about that for now, about the radiative transfer, because it's a bit beyond what I explored and I studied about simulations. So sorry, I cannot comment much about that.
No problem. Thank you very much.
Yeah.
Hi, just a quick question about this point that you were just mentioning about the multi-phase and multi-structure of these AGN-driven outflows. Maybe I missed that. In the sources that you are observing on these atomic lines and the recombination lines, I guess you also looked at the molecular component,
yes.
at least in molecular hydrogen. So I was wondering if you see these different structures, both in the spatial, in the morphology, and in the kinematic component, and if there is any plan, since you mentioned it, to use ALMA, or if there is data existing on CO, for example, and if you have this multi-scale, multi-wavelength picture of an outflow, at least in some of the sources that you showed us today.
For the quasar feedback survey, we have ALMA data that I'm not the one analyzing. The paper is in prep by a PhD student as well, so it should come out in. And for the ALMA, we are currently seeing. I don't have the figures easy to show, but I don't know if I can show them anyways. But for the quasar feedback galaxies, we are seeing two things with ALMA. We are seeing compact outflows in the nucleus, and we are seeing really extended 10 plus kiloparsecs filaments that we think could be signatures of outflows as well, but we are, I don't know, I wasn't 100% convinced they are, but we have this multiphase picture for this for at least 2 or 3 galaxies in the quasar feedback survey. For NGC 7469, it is harder to disentangle the outflowing component of the molecular gas because it doesn't have a very clear blue shifted wing or a very clear broad wing on the line that we could easily disentangle. But what I can say about the CO maps about this galaxy, on the kinematics, I don't think we have the information yet, but we have the flux map for the intensity map for the CO, and it is basically equal. The distribution of the CO is basically the same as the distribution of the molecular hydrogen. About the kinematics, I don't have I think our spectral resolution wasn't good enough because I wasn't the person carrying this kind of analysis. One of our collaborators did that, so I cannot say much about that but for another galaxies that I studied with NIFs, one of them had some published ALMA results, and they saw nuclear compact outflow, and we saw the exactly same counterpart with a different, the velocities were a little different, but the extension was a bit larger for the molecular hydrogen. And we saw the same compact nuclear outflow that people saw before in ALMA. So there is this connection exists.
Okay, thank you.
Okay.
There is another question.
Great. Thank you.
Hi, thank you for the excellent talk.
Hi, Stella.
I have a more basic question. And when you said about the quasar feedback survey, can you explain more about what is a type 2 and a type 1 object, please?
Okay. A type, I didn't put any pictures about that because I have mixed reactions when I show the unified model of agents pictures, and some people like it, some people really don't like it, so I didn't put anything about that. But in short, a type 2 agent is one an agent that has the basic structure, has the supermassive black hole, accretion disk, and the torus, the dusty torus, basically, and jet or no jet, depending on the galaxy. A type 2 agent is the one that the torus is blocking the view of the inner region. So we don't see broad emission lines, broad components on the emission lines for the recombination lines of the hydrogen, H alpha, H beta, Paschen alpha, Paschen whatever, helium lines. You don't see any of the broadened component because the density of the gas is larger at the center. So you see that this broadened closer to the nucleus in the region that is within the torus. In a type 1 source, you could see it in an angle or completely face on this structure. So you are seeing inside, you are seeing the mechanism from the inside. So you see these broadened components. On the case of the quasar feedback survey, we have the data for the type 1 sources. But since the H beta and all 3 lines, they are so close together in the spectral range, if we had this broadened component on the H beta, it would contaminate those 3 lines as well, because in some cases it's really broad, like 4,000, 8,000 kilometers per second in the full width at half maximum. So it's really broad line, and it could contaminate the other line. So to make the analysis a bit easier, we decided to just drop the type 2 source, the type 1 sources, and analyze the type 2. I don't know if I was clear enough without showing pictures.
It was very clear. Thank you.
Okay, yeah, it was super clear. Thank you for your explanation. And I am just curious, and I am just going to make a last question. When you were presenting your targets for the JWST data, you were showing the pictures of some of your targets, and you mentioned that there was one who has 2 nucleus. Is that correct? Can you comment?
Yeah.
Okay.
Yeah, that galaxy is really cool. It is an ongoing merger. I think this one I can come back to the show. Oops, not this one. Window. Okay. This. Okay.
Yeah, there it is. I went back to the first.
Yeah, because I
yeah
from curve. Oh, yeah. NGC 3256 has 2 nuclei. If you to the unadvised eye, it just looks like a normal. It could look like a spiral galaxy with a dust lane on the center. This darker region, but actually it has 2 nuclei, one on the northern part and one at the southern part. I can comment that that's why we know they have 2 nuclei, so that's why the two pointings for the spectra, the images we have for the whole system, but I can comment that I think it is the south one, or one of the nuclei has very interesting activity going on in terms of outflows, but the other shows nothing.
Okay.
And I think both of them are agents, but one of them has really cool things going on and the other is kind of boring.
Okay.
And these other galaxies, 2386 and VV114, you can also, this galaxy has, 2386 has 2 or 3 compact sources in this region, and maybe one of them is the actual nucleus. We don't see any agent signature in that yet, so the paper for that will also come out in, I don't know when, but it is in prep. And for VV114, I think we also see really buried more than one point source, compact source in this galaxy, but none of them showing clear agent signatures as well. So, and GC7469 is only the clear agent, but this one is an ongoing merger. All of them are mergers, merging systems. 7469 is the one that has the merger, the companion that is the farthest apart. So
Okay,
different
I see.
merger stages.
I see. Okay, well, thank you for the clarification. Thank you so much. And, well, let's close. Thank you again. I may give a applause to you here. And, well, thank you. Thank you very much.
Thanks, Maria. Thanks, everyone, for the questions and for your time listening to me.
Great. So, Richard, we can stop the broadcast, please.